Hello everyone, we have Evin Pinar Ornek with us today. Evin graduated from Boğaziçi in Turkey, and even as an undergrad, she was very active. She spent some time at Google, KU Leuven, and MICCAI for Intelligent Systems. Evin is currently a final year PhD student at TUM. She's finishing, apparently she submitted her thesis. Good luck with the presentation. She's working with Federico. You remember Federico, he gave a talk here recently. Her research is very interesting, focuses on indoor 3D scene understanding for robotics and AR/VR applications, zero-shot learning in 3D, scene representations through semantic scene graphs, and the relevant tasks in spatial reasoning and generative modeling. Her has a very, very interesting CV. She did lots of internships at Apple, Meta, Amazon, and so on. You can talk to her about these experiences and the things she will present today. I'm looking forward to her talk. Thank you very much for accepting my invitation.
Thank you for inviting me. It's great to be here in Istanbul in Koç University and talk about my research. So since we have gone through the introduction, I will just start with my talk. And during the talk, you can ask questions. And after the talk, I will be happy to answer any of your questions about any career-related things, for example. And my research over the PhD can be titled as From Unseen Objects to Holistic 3D Scene Understanding.
Is it not changing? I
think not changing. Okay. So when we say 3D scene understanding, and especially holistic 3D scene understanding, what we actually mean is human level understanding. For humans, understanding in which environment we are, what is happening there, what types of objects there or humans are there. It's really easy. It comes without an effort almost. And usually a single glance is enough for us to understand what is happening in a scene. For machines and computers, it is not as easy yet. And it would be great to have such abilities also to have for machines for various applications. For example, on the left, I share a mixed reality teleconsultation setup. This is in Munich. It is a simulation room, and it is actually in a hospital. And I spent my first year of PhD in that simulation room. And here the application is, so we see a local patient and a local doctor. And in case they need an assistance from a specialized doctor, the idea is that they can connect to this remote doctor via teleconsultation system. Remote doctor can wear a VR glass and can see himself within the environment, within surgery or patient visit. And the local doctors can see their overlays through an AR glass, like a Microsoft HoloLens glass there. And there was a demonstration during COVID pandemic, which was a nice use case for such an application. On the right, you see a robot, like a tiny robot. It's a household robot. It is currently still under research. It is in Amazon. And it is used for like indoor monitoring, surveillance, and assistance. And during my PhD, I spent a bit of time at Amazon during an internship, and I worked on this robot. And scene understanding could enable such applications. And today, this is the overview of my talk, also my PhD. I will talk about two main groups of papers. First one is unseen object recognition, and second one is holistic 3D scene understanding. There are 3 papers each. I will briefly talk about them. Then I will summarize and try to give the main ideas and main conclusions out of these research activities. And I will talk more in detail about the most recent works from each group. And starting with unseen object recognition. So to be able to understand scenes, we need to start with objects. We need to understand which objects are there in the scene. And in this case, I share some virtual reality interesting applications. If we would be able to understand and classify and track maybe any type of object in an environment, we would be able to maybe introduce these various types of objects, for example, a tennis racket in a VR system or a pottery. And it could enable like teaching a pottery, a teaching assistance system, for example. Or we could even play some tele chess game by introducing the chess pieces into a VR. It would increase the haptics, and it would make our experience, like VR experience, more realistic. But when we look at the stages of an object recognition method and any like supervised machine learning method, usually there are two stages, the training and test. Training is a computationally heavy stage. It requires a large training data set, multiple GPUs, perhaps hours or even days and longer. And at test time, we want to run them in ideally in real time in several applications. Can be semantic class prediction, segmentation, could be also 6D pose estimation. So during training, we have a set of objects, specific objects, and at test time, usually we cannot predict the other objects that were not included at this training stage. And zero-shot methods aim to recognize these unseen types of objects at test. So the classes that were not seen during the training. My first work, 3D composition zero-shot learning, aims to classify and segment 3D objects in zero-shot manner. And here, to be able to do this in zero-shot, we use the idea of compositionality. This concept, actually, like there is some research on 2D, but we were kind of first to show that it was useful also in 3D. And actually using 3D data makes more sense because we can observe the full object with all of its parts. Now, the idea is we have a set of seen objects like a display and keyboard where we can learn the parts from, like a display screen, key, a horizontal surface. And at test time, when we encounter a novel object with these seen types of parts, we can segment this object to a set of seen parts. And if we know that, for example, a laptop includes actually a display screen and a key, we can directly identify its class by using this prior. And yeah, this is the main idea. And to solve this problem, we had a method which tried to first compose the objects into their parts, so segment them into their parts and decompose them like Lego blocks. So, if we are able to decompose this object to the intended object class, then it means that it is in fact that object class. And therefore, we had like a two losses, segmentation and classification. And we named our method a decompositional consensus because we want to have this consensus between classification and segmentation. And we created a data set and showed that the proposed method works, whereas the 2D counterparts would not work. Next, next paper is about zero-shot instance segmentation. This time we want to have a class agnostic instance segments, and we make use of multimodality, so RGB and depth data. This setup looks like this. Again, we have a train set with seen classes, can be a plate or a mug, for example. And at test time, we encounter both seen and unseen type of classes like camera and printer. And we want to be able to learn a segmentation from a set of seen classes. And we want to generalize this to unseen classes. The idea of using this RGB and depth data is because they're actually complementary in nature. From depth, we can directly understand the occlusion boundaries, the objectness boundaries around the objects. But in cases where the depths are very close to each other, for example, a poster on a wall, the depths are very similar, we can take use of the images because images would provide us with the textures and through the gradient changes, gradients. Here, the solution was to use an approach similar to graph cuts, but graph cuts kind of first applies a superpixel on the image, then tries to connect these superpixels together to form objects. It is the normal optimization method, non-learnable method. We replaced graph cuts with a learnable version where we had a couple of MLP layers, which learns this connectivity between the edges. And up next, I try to solve the unseen object 6D pose estimation problem. In this case, this pose estimation problem is a bit more difficult. It's a bit more lower level than classification or segmentation. And here, we need to somehow simplify the problem. And for this, the assumption is to have an onboarding stage, which is limited to a couple of minutes, let's say maximum 5 minutes. And through this onboarding stage, we try to introduce our new object to the system. Therefore, it can detect and track the object in real time at test. And so we move from zero shot to few shot setup. Few shot machine learning methods rely on this, such an onboarding stage usually. And unseen object pose estimation with foundation features. It's FoundPose. Now I'll talk a bit more in detail on this paper. It is presented at ECCV 24 this year. So what is model-based 60 pose estimation? So here we have a CAD model of an object in model frame, and we have an image where this object appears. We want to be able to register this object within the image plane by solving or estimating the rotation and translation parameters. We have 3 rotation, 3 translation. And this project is done during my internship at Meta Reality Labs. And here is the application that they were looking for, is to introduce our natural objects like a pen, keyboard, or a mouse into VR system to increase the immersion. If we would be able to track our keyboards, then within the VR environments, it would provide us with some natural input. When we look at the literature, the object pose estimation problems can be divided into 3 problems. First one is the just regular supervised training. We have a training stage and a test stage. And this test stage, we can only track the scene types of objects. Then we have problem 2, is the model-based pose estimation of unseen objects. Here we have the onboarding stage, and we want to introduce these novel types of objects. Then we can track them. And problem 3 would be the more difficult scenario of model-free pose estimation of unseen objects. So here we don't even have the CAD model. Instead, we have a set of reference images where the object appears, and we want to be able to track that same image on different set of images by learning at that stage. In this project, in FoundPose, we target problem 2. And the idea is if we have a robust solution for problem 2, we can also maybe solve problem 3 easily by assuming a reconstruction of an object. But problem 2 is actually very challenging because first question is how to quickly onboard new objects within this 5 minutes limit. And second one is how to bridge CAD to image domain gap. So these CAD models are synthetic models, and we don't actually have any images that contain these objects. So it is a fully synthetic domain. And at test time, we have real images. This domain gap, in the previous work, it was tried to be mapped or addressed through using a large synthetic image dataset. As in MegaPose, they have 2 million images with 50,000 different object types to enable generalization.
All with CAD models?
All with CAD models, and images look like this.
Do they tell you which object to focus, or are you responsible for all of them?
In this problem, we know which object we are looking for. So, and they create such rendered images, these synthetic images. They learn how to register the pose, so how to estimate the pose parameters from the synthetic images. And the assumption is at real time, we will have similar images to such images. But actually, there is still a bit of a domain gap. Now, with FoundPose, we, instead of using such a large synthetic data set, we used a frozen DynaV2 model. DynaV2 is a vision transformer-based vision foundation model. It is trained in a self-supervised manner on a curated dataset of 142 million images from diverse sources. And it has been shown to work for various computer vision tasks, either off the shelf or with a very minimal fine-tuning. It has been shown to encode semantics, encode geometry, and also be used for establishing correspondences across different domains, like in a real image and some caricature or a hand drawing. With FoundPose, so we have two stages. First one is object onboarding. Second one is the real-time estimation. During onboarding, we have the CAD model, and we first render a set of templates covering different viewpoints to see this object. For each template, we extract DynaV2 feature maps. Also, we can also have depth maps, which can be used for 2D, 3D correspondences. With the extracted DynaV2 patch descriptors, we create bag-of-word descriptors. Bag-of-word is a very classical method. It comes from the natural language processing, but then it's also used for vision understanding and retrieval tasks. It simply creates statistical vectors to show how many features appear in an image, how many of each feature, let's say. So for each template, we can create this descriptor vector. And at inference time, we have an input RGB image. We first segment this image by a method called CNOS. CNOS is based on SEM, so it can actually segment any type of object. We get we warp the image a bit and get like a crop centering the object within the frame. Then we extract the DynaV2 features, create a bag-of-words descriptor for the test image, and then try to find the most similar looking templates by simply vector similarity search on top of our created object representation. We get like a couple of templates, let's say 5 templates. These templates actually provide us the most similar looking images to the objects given in the test image. After we have that, we do the feature matching on top of DynaV2 features again, in between every template and the test image. It is a KNN search, like one-to-one search from one image, from test image to template feature vector. Then once we have such a 2D correspondences, since we also have the depth map from the CAD model, we can use 2D, 3D correspondences to estimate the pose via PMP Ransack. And finally, we have an optional pose refinement. We call it a feature metric alignment. It is based on Levenberg-Marquardt optimization, also common in SLAM. But this stage is optional. And without even this stage, we show that it is possible to get a coarse pose estimate of the object. And so in this case, we didn't have any training, and we used only DynaV2 features with a classical set of computer vision techniques like bag-of-words, PMP, feature alignment to establish state-of-the-art pose estimates.
So I think I have a question here. Did we talk about this, or did I talk to Thomas the last starter? I don't remember, but this is a very traditional looking computer vision pipeline.
Exactly.
Did you have a hard time with the reviewers? Were they like, why is it not end-to-end or something like that?
Yes, actually, our work is rejected from CVPR because of this reason.
Exactly.
Yes. But in ECCV, there were a different set of reviewers, and this time they appreciated, and this was even a positive for them. That there was no training.
Because I think it's a good learning experience for all of us, right?
Yes.
You have such a paper. Knowing these things and putting them together, making it work must be also a lot of effort.
Exactly. Yes. In the beginning, it was a question for us as well. Like, we want to use DynaV2 features. Can we get as good result as the ones that train on the synthetic image data? Like how much we can push? First, we saw, okay, it is possible to get correspondences, but they can be a bit noisy. How to improve this? Maybe we need a template retrieval using templates. It's already an existing idea. But then how to retrieve these templates And this bag of words method, like there are these stages. And I think to show this to reviewers, one of the things was to compare with the other methods in terms of computational expenses and data very clearly. How much memory is required for the object representation, for example, and how much memory do other methods require?
Is it the rebuttal or in the original paper?
Partially rebuttal, partially original paper. Like both memory, speed, all considerations, all in detail, very clearly. When you present them and show the advantages of the method, they were impressed. Yes. And here are a set of results on different types of data sets. LMO focuses on occluded objects. HB has some objects like toys and so. ITAL has mechanical parts. Here we show the occlusion, the object estimate of pose estimate boundary, as well as retrieve templates and the features of the real image and the template and the correspondences. And here it becomes more visible, even though the real image and the template, so the ones in the second row, are of different domains. Their features, the high-dimensional features, are actually look more similar to each other. So it is possible to establish correspondences in this high-dimensional domain. And I thought is challenging data set because of these mechanical parts, shiny objects, symmetries. It was interesting to see that even in that case it works.
Do you guys not have any questions I keep up? But Dino is a patch level method, right? How do you achieve pixel level accuracy with Dino?
There are a couple of things. First is we try to increase the resolution as much as possible, both this test image and the templates. That's the reason why we center the detected object in the frame, and then we apply this upscale the image. And this is one of the things. A second thing is, I think, I think that only that worked. We tried also, for example, the vision transformers with that kind of stitch the different resolution feature maps together. It increases the dimensionality, but it becomes more pixel aware. In this case, we saw that this was not necessary. It was increasing the memory too much without not improving the results much. And one of the things was the Dino V2 with registers. So there's this Dino V2 paper, and they also have an update on that paper. So there were these noise around the features that were discovered, and they added like an additional kind of a bank within the transformer to collect all these noises. When we changed our backbone from Dino V2 to the one with registers, suddenly results also improved, which showed that this noise was actually also noise for us, and they were not very useful. I think this also improved. Whereas, interestingly, in some applications, this noise was useful because they provide positional encodings. And especially like reconstruction and generative modeling tasks, they found these noise to be helping. So it is also it's good to keep in mind that depending on the application, what you think may not be very, what you find that is very intuitive for yourself may not actually be the case. So it is always good to try a different set of things.
That's another question.
So for the initial rendering part from the CAD model, do you have this number of images or do you?
Yes. We have like around 400 images.
For the selection of the yields, do you just uniformly sample around the object?
It is a uniform, so all these 400 images, they're uniformly sampling around the sphere of the object. When to select the most similar ones, we use this bag of words retrieval.
For correspondence point tracking, long-term point tracking problem, we found stable diffusion to work better, especially on synthetic-like datasets. Have you tried that one?
Stable diffusion we didn't want to try because it is a larger and more costly backbone. Also runtime is higher. Here we can achieve real-time application. It is also, so DynaV2 itself is also a large model, but when we move from the large model to smallest model, you can already gain a lot on memory. Then it is also possible to distill the model even to a smaller network, which could be fit in a smaller mobile devices. Yes, you can apply quantization, and there are many different tricks.
Are they doing it right now after you left?
I don't know.
They don't talk to you anymore.
It is also possible to apply. There are also like quantized diffusion models and maybe like faster diffusion models nowadays. So it could also be another direction. Yes. Okay, so this completes my part on unseen objects. Now I'll continue with scene level understanding and move towards holistic 3D scene understanding. So on the left, we have an image, RGB image, and a depth map that is acquired by the depth sensor, Kinect Azure sensor. It looks like this. And we can unproject the depth map to a point cloud, as on the right, by using the camera parameters. And once we have this kind of 3D representation of the environment, we can collect many of them, apply reconstruction, get a full 3D representation of the room. Then to understand the scene, we can run numbers of problems or tasks. These tasks focus on different things about the scene, but eventually we actually want to be able to understand the scene in a human level, really try to understand what is happening there. And there are many tasks starting from object detection, segmentation, scene classification, scene reconstruction, depth estimation, and moving to layout estimation, relational contextual understanding, optical flow, tracking, and there can be even things like visual question answering and so forth. In the first work, I worked a bit on monocular depth prediction. It was also my master's thesis topic, and it was one of the first publications. In this case, here we see a depth map acquired by the sensor on the left top image. And on the below, we see the point cloud, an unprojected point cloud from this acquired depth map. We can train a monocular depth prediction network with a set of images and depth maps that look like that. And then we can run this depth network on a real image, and it would predict the depth values, which is usually visualized as a 2D heat map representation. But when we unproject it to 3D, we end up with somehow undesirable result. You will see the occlusion boundaries around the objects are interpolated, and it does not reflect the reality. And this is
supervised. Is it supervised?
It is a supervised method. Here I use the supervised method. It is single image training. And this is an artifact that still exists. We did this research work on 2021, but still, like, there are state-of-the-art methods that can achieve very nice looking depth predictions. But when you uplift lift them to 3D, they usually have this problem on the occlusion boundaries, this artifact. In the depth map, it looks quite sharp, but on point cloud, it is not as nice. In this project, we try to improve this artifact a bit. And we try to use this object awareness. The idea is the first idea was there to detect all objects in the scene, estimate their depths, and kind of stitch these separate depths all together. But there is no such an object estimator method that can detect all possible objects in an environment. Instead, we used here superpixel segmentation, which is an off-the-shelf unsupervised segmentation method. It creates these segment patches by looking at the gradient changes in the image. Once we extract the superpixel masks, we can run a normal like a convolution. But when we run convolution, there's also a problem there. The convolution operator, how the window traverses on the image, it does not separate whether the pixel is coming from one object or the other. It applies an averaging operation. So we found that to be another issue, and we come up with so-called instance convolutions. Instance convolution calculates the convolution only on the regions where the mask exists. So for each superpixel mask, there is a separate instance convolution calculated within this network.
Was there deformable convolution at the time?
Yes, it is. This is also an inspiration for us. Exactly.
Did you try it as a baseline then? Or?
It doesn't exactly fit here because it's still deformable convolution, I think. So sparsity invariant convolution was another one. They are very similar ideas. Here, the difference is we convert all the superpixel masks to binary, like 0, 1 masks. And convolution, the calculation of the convolution only considers the center of the mask and looks at other pixels. And if the center is the same with other pixels, then it says, okay, we consider them, otherwise no.
But convolution could learn it in principle, right?
Yes, that's also true.
But it
Maybe.
was not suggested as a function. It was
not an idea to try it as a direct replacement. Also, the other differences, these instance convolutions don't work off the shelf. They are not able to predict the depth values directly. You need to add them to a backbone, like a pre-trained backbone, and use a couple of instance convolutions after this and fine-tune this backbone along with the instance convolutions. Eventually.
So in that case, are there any downsampling in this convolution network?
No, there's no downsampling. There's no upsampling. It takes the features at the exact same size and it applies the convolution at the same size. Exactly. Yeah, here we have on the first row, we have the ground truth depth map and point cloud. On the second, we have a sharp net. Back then, it was the state-of-the-art method. The occlusion boundaries are very blurry, very visible on 2D also here. And the 3D, it is just an interpolation. And this proposed method, instance convolution, improved this occlusion boundary problem visibly on 2D maps and slightly on point clouds. The more interesting results, I think, we also tried it on Kitty dataset. And here we have a pedestrian in the image, which was not detected in the state-of-the-art method. But with using this instance convolutions or object awareness, suddenly the pedestrian becomes available on the last row. But yeah, as I said, I think this problem is still relevant for today's state-of-the-art methods. Maybe now they're at larger networks, they're a bit more difficult to fine-tune. So maybe instance convolution is not an exact solution, since these networks are already costly. But one needs to be aware of this 3D structure and the occlusion boundaries when training a monodepth network.
Is the most just the same, like that one?
Yes. Okay, now I will continue. Again, in scene understanding, I will talk a bit on 3D semantic scene graphs. A semantic scene graph is a data structure that organizes the entities of a scene in a graph where objects are nodes and their relationships modeled as edges. Here in the scene, we see two objects, two chairs. They are the same type of chairs, so we can attach them together with the same as relationship. One is in the front of the other. We have the front relationship. Here we have the floor also as a node, and we can put chairs on the floor by adding a standing on relationship. And this 3D semantic scene graphs, this is a topic that is very well researched in our lab, especially since 2020. But like before then, there was research on 2D semantic scene graphs, and it has been shown to be useful for many different tasks, from reconstruction to scene understanding to retrieval and so. Because it is a very compact representation which captures the gist of a scene. You can represent the entirety of the scene with only a set of nodes and relationships. In our case, we used semantic scene graphs for operating room domain modeling. So this is the simulation environment that I shared on the first slide. On the left, we have a set of images, multi-view RGB images and depth videos. We have 6 Kinect Azure cameras attached on the ceiling of the simulation environment, and we simulate knee replacement surgery. We have the depth maps, and the idea is to be able to understand what is happening in the scene via a workflow phase prediction, in which phase of the surgery we are in, and by also detecting the roles or predicting the roles of people. Who is the head surgeon? Who is the circulating nurse, assistant surgeon, and so. And we do this by first predicting the semantic scene graph. I don't share the entirety of the methods or pipeline, but the idea here is to segment all the objects, also people, along with their poses. Once we have these nodes, then we can train a network to predict the scene graph. So the classes of the nodes and also the relationship between all these nodes. We classify humans as humans, not their exact roles in this case, in this stage. And at the second stage, we try to predict the humans' roles as well, and also the phases of relationship by considering temporality as well. We presented this work at MICCAI, it's a Medical Image Computing and Computer-Assisted Intervention conference at Orals, and we have a set of works.
Considered medical imaging.
This is kind of both. Yes. Also, the journal extension of this work got a journal award, which was very important for us. It shows that there's a future in this research. And so we show that scene graphs can be used for such a complex operating room surgery type of understanding. Next, we use the scene graphs for generative modeling. And the goal is to generate common living environments like a living room, a dining room, or a bedroom with its entirety, so fully in 3D. But this is not an easy problem, because usually when we design environments, as humans, we kind of like ensure that the objects are consistent with each other, with the entirety of the scene. When we place 3 chairs, we usually have 3 same type of chairs. When we try to put a table in the middle of the chairs, we make sure kind of to have a similar or shared style. So this establishing such scene object and object consistency is a bit challenging. Also, since we want to have this generative model, it should be diverse enough. At every separate run, it should generate us a new environment. It should not just retrieve a set of random objects, or it should not generate the same objects at every separate run. And we address this question, so 3D scene generation, by using scene graphs. The assumption is user can provide a scene graph, like it can suggest to have 3 objects, a bed, chair, and wardrobe. Bed should be on the left of the chair, should be close by, shorter. Wardrobe should be on the left of the bed, which should be taller and bigger. Once we have such a scene graph from the user, we generate a 3D scene that is consistent with these with the scene graph. Practically, it is also possible to take a natural language input, like a sentence. One can then convert it into a scene graph, then it is run our algorithm. And in core, we actually have input scene graph and output 3D scene. In core, we have a variational autoencoder, which tries to reconstruct the layout and the shapes. And step by step, we have the scene graph. The object nodes are represented as one-hot vectors, also the relationships. Then we update this one-hot vectors with contextual input. And here we use clip embeddings to improve these node representations. And then we input this to a graph variational autoencoder to learn the distribution of the scenes.
So Evin, here you are generating the scene in a single shot or in an incremental setting, like you first generate the bed and then add the chairs?
So it is an incremental nature, but it is not an autoregressive method. It is just, so it is also possible to generate them at a single run, but since memory-wise it would be costly, we just generate them one by one. We generate the shapes and layouts all together at the same step. Then we infill the boxes with the generated shapes.
I have a question.
Yes.
Would it maybe one can achieve more diversity if you're generating the graphs, right? You're generating from graph, condition on the graph, the scene, right? Would it be, if you have like the stochasticity in the graph kind of thing, any graph can be decoded with a frozen decoder, let's assume, to the corresponding scene, but the variety is actually in the graph itself, maybe. Or do you want variety or diversity in the shapes? From the same graph, you should be able to generate different shapes, not the configuration itself,
yes,
but the, how the thing looks like and so on.
Exactly.
Is this what you want, or is
this is exactly what we want?
You don't want? It's a different problem than diversity in the
diversity in the locations of the objects. I think it's a different problem. It is also relevant. In this case, we want to constrain the environment with user input. So through scene graph, the user can suggest a very coarse level layout, like arrangement of objects. It can say this. So it does not induce, the user does not say, okay, at XY location, there will be this object and YZ this object. But instead, some very common, like coarse arrangement, and then we generate this different arrangements that are consistent with the constraint. But it is also possible to, generate very random graphs. So there are also methods to generate graphs. So we parameterize the scene in terms of layout. In layout, we have boxes of objects, size, width, length, 3 dimensions, location, x, y, z, the center of the object. And also here we assume a single angular rotation parameter. We assume the objects are parallel to the ground. And we use a simple L1 reconstruction loss. For the shapes, we use a sign distance function representation, and we learn them through a diffusion model. So this diffusion model is like similar to stable diffusion, but instead of 2D, it operates on 3D, and there's a 3D unit, and it generates the shape in terms of voxel. Within the voxel values, we have the sign distance values of the object. And there are some works that do this by conditioning on text. For example, I can say the diffusion model to generate a bed, and it generates a 3D bed. But in this case, we don't want to generate a random bed or a random table. We want this object to be consistent to the entirety of the scene and to other objects. For that, we condition the diffusion model on latent graph embeddings. So these are latent vectors that are the output of the graph convolution network. So in graph convolution network, there are a couple of convolutions that do message passing. Through this message passing, these latent vectors become aware of other objects, their relationships. So now they're not focused only on this. They are not one-hot vectors, but they are really aware of the entirety. And we use this latent embedding as a conditioning. We do both concatenation in the unit and also cross-attention to condition and generate the shapes. Then we train our network all together with the shape learning and the layout construction, and run at a single stage, generate the boxes, and infill the boxes with the shapes. And the generated scenes look like this. We have a scene graph, top-down view rendering of the scene, and the generated scene fully in 3D. For evaluating, we use a set of metrics like scene graph consistency, whether this generated scene follows the constraints within the scene graph, but also we check FID, KID scores of the top-down renderings. And also like object levels, there are object level metrics like chamfer distance, and they're also like used for evaluating the object levels, generative abilities. Okay, so this concludes all the papers. Now I talked about object level understanding, scene level understanding, a set of different problems and methods. Now I want to kind of summarize the main takeaways, the key points. So first, we showed that unseen objects in 3D can be recognized by a set of concepts. So we can alleviate this data challenges through compositionality, as in compositional 3D learning, through multimodality, as in SupeRGB-D, which used RGB images and depth maps, or through 2D foundation models. So these foundation models are not trained on 3D, but they can be used for 3D tasks as well. Second, this complexity of the scenes can be captured as a whole via semantic scene graphs, and we show that they can be used in a various level of like complex tasks, from role or workflow prediction in operating rooms to 3D scene generation. And finally, I think this is an interesting outcome. All methods we used had a sense of compositionality, and they are towards holistic scene understanding. Here, the compositionality and holistic understanding are kind of clashing concepts, because compositionality suggests that we can understand a whole by looking at parts, whereas the holistic understanding is more interested in understanding the overall gist of a scene. Here, we used our methods were compositional, but they were for holistic understanding in unseen object recognition, improving the monocular depth by superpixels, using semantic scene graphs as object awareness for scene level tasks, or the examples of the methods.
If you were starting a new project, would you go this bottom up or top down?
So both.
Exactly.
Exactly. Especially, I think, the generative modeling, generating an image or a scene with multiple entities within a complex relationship to each other is very difficult. There's also a benchmark and stable diffusion like generative models. When you suggest a network to generate, I don't know, 5 people, it may or may not generate 5 people. For this, we need compositionality. And there are like some future directions, either like a direct direction on top of our works, or longer term questions and directions that I'm very interested in. First one is on top of zero-shot learning and unseen object recognition, there is the open world recognition. There are some existing works that use language models to connect this semantic understanding to vision, but semantics are fuzzy. It is a fuzzy term. There are synonyms, class hierarchies, domain-specific names. So these are the things that need to be discussed or addressed. And also, for example, segmentation, the granularity is not very consistent, especially in like the state-of-the-art segment anything model, it gives nice segments, but there is no granularity, the consistent granularity. This could be inputted by user, for example. Second thing is about generative modeling. I think the CommonScenes, so we had another work after CommonScenes, EcoScenes. There we also try to generate the texture of the objects to make them look more like to real environments. But I think this can be improved even more with reconstruction goals, and especially with novel wave synthesis, NeRF or Gaussian split kind of representations. And they would enable more data kind of for free. So one can use these novel wave synthesis methods to generate 3D data. Then this 3D data can be used for generative training. But they also use so generative models also support novel view synthesis, especially on the views that are completely out of the input data. They help on this completing the hallucination. So there's a kind of a mutual benefit. And finally, 3D foundation models would be, I think, this is the direction that we might go to address all these separate type of challenges. But then here the question is, should it be trained only via images, or do they require the 3D data? If we use only 2D images, it might be more easier. We have lots of 2D data, but what type of tests do we need to train these models so that they will have a 3D reasoning? This is a question. But if you use 3D data, then how do you collect all this 3D data? How you annotate the 3D data? And which type of representation you use in 3D are questions. Do you use a mesh, point cloud, a voxel? I don't know. There are many different ways to represent 3D. There's no unified representation. And nowadays there's this spatial AI concept, which kind of asks whether it is possible to have a human level spatial intelligence or understanding for computers. I think it will be enabled only after we answer such problems, like have a better generative plus reconstructive methods and address the data in 3D especially.
Thank you very much, Evin.
Okay.